So is my screen up for you? Okay, well, let's get going. Then let me start out with some acknowledgements. This is not a solo effort. I'm doing the presentation, obviously, but the ideas here were formulated to a large extent by Tom Neal, who initiated the timber grading training workshops. We've done 5 of them so far, and started in 2014, a couple times in Heartwood. There was one out in Coeur d'Alene, a couple in Denver, maybe 6, and one in South Carolina as well, I think. Ron Anthony is our primary instructor as from the perspective of wood science, and he's taught at all of them. And we always have a certified grader from one of the grading agencies, one of the rules writing agencies, to participate in that workshop. Duncan, my partner at Fire Tower, and I are co-authoring an article for timber framing on this topic. And so we're doing this presentation in part to try to solicit or stimulate some feedback, so maybe we can make the article more complete. And so Duncan's contribution has been with regard to review of the content, and also he developed all of the illustrations here. So again, we kind of conceived this work back in 2015, and certainly it's taken a while to actually make it happen. But after participating in 3 grading workshops, I think I finally have a handle on how it works. And if you've only been to one and you understand all of it, I'm really impressed with your ability to learn and absorb these techniques. So that's kind of what we're doing here, is to review this stuff. Duncan is, I think he's on, or at least he said he would be on. I didn't see him on the roster. I know Ron is out there, so they're going to be able to help answer questions. Tom as well. Tom's got extensive field experience doing this kind of stuff. So what's the objective of stress grading? We're going to start kind of with a higher level overview and then drill into focusing on just nuts. So our objective when we stress grade a timber, whether it's one of us or whether it's a grader in a mill, is to obviously make the most economical use of the timber, of that resource, is to avoid unintentional or unnecessary use of high value material, and properly account for the primary strength reducing characteristics. Those consist of the knots and the slope of grain. The primary focus of this presentation is on knots, but I've got a few slides at the end where we can talk about slope of grain if there's time. So before we're moving on, it's important to accept a basic premise that we're talking about wood, and so there are no absolutes. And so, as I mentioned already before we started, as Ron likes to say, everything is a rule of thumb. So don't be surprised if you find an exception to one of these rules as we move through. There's a reason that we grade timber and lumber, and the primary reason is it's the law. The local building code, assuming that it exists in your jurisdiction, is often the International Building Code or the International Residential Code. That refers to the National Design Standard for Wood Construction, which refers to the grading rules from the various grading agencies. Those rules are approved by the American Lumber Standards Committee, which certifies their conformance with Public Standard 20. That's the American Softwood Lumber Standard, which refers to ASTM standards, and in particular standard D245. So this is an important hierarchy to review, but you don't have to memorize it. I'll make the point that's important in just a moment. Recognizing, and the American Softwood Lumber Standard is for lumber, but fundamentally the same rules apply to timber. The good news here is grading agency have mostly agreed on the grading rules. They have harmonized on a single set of interpretations, and that essentially means there's one method, or we can use one method, a consistent approach for measuring knots, and regardless of which agency puts its stamp on the stick, or whether it's lumber or timber, a knot is defined in the same manner. So there could be slight variations in the definitions and rules for knot measurement, but we'll talk about those developed by the WWPA. The Western Wood Products Association is in Portland, Oregon. It has 2 books that you need. If you're going to do this work, you need both of these books. Normally the one on the left, the Western Lumber Grading Rules, is the one that tells you how big a knot can be, what's the slope of grain, how much wane can you have, that sort of thing, for a particular grade. It also has definitions in the back, in particular definitions of knots. The grading interpretations has illustrations, some of which we're going to be seeing today, as well as descriptions of the grading rules. So you really need both of these things. First, let's talk about how knots affect strength. The knot wood, the actual content of the branch that remains in the tree, is not the weak link in a piece of wood or a piece of lumber or timber. Instead, it's the fibers that grow around the knot have a localized slope of grain, and if we apply load to a member, let's say tension, direct axial tension, or compression parallel to grain, or bending, then the failure, if a failure is going to occur in the vicinity of a knot, it will be in the wood around the knot due to tension perpendicular to grain or shear. So generally larger knots cause larger grain deviation, and as a consequence, larger knots lower the grade of a stick. Before I move on, I'll note that the grain deviation around the knot is not measured in the same manner as slope of grain. It's considered to be a different characteristic. So I've got a side view of a big timber with a couple of small knots in it, and the little purple arrows point to the growth lines as they move around the knot. Clearly, that's the grain deviation. So let me illustrate then how that might result in failure. These are pretty small knots, and it's probably not going to be a problem. They're probably not going to be a problem. But if we apply axial tension parallel to the grain of this stick, then the resultant stress, let me turn on my laser pointer. The resultant stress is a horizontal vector, the red line. That can be broken into a shear component that acts parallel to the growth ring, and a tension perpendicular to grain component that acts, well, perpendicular to the growth ring. Wood has low strength in both shear and tension perpendicular to grain. So if we get a lot of these, a lot of grain deviation, it can lead to failure of our sticks. Some examples of slope of grain, or I'm sorry, examples of failures around knots but not in the knot. In this particular case, these are photos that Ron shared with me of tension tests on lumber with knots. In this first one on the right side, you see a fracture that indicates the slope of grain failure, perhaps associated with grain deviation, or maybe it's just a more general slope of grain failure. But nevertheless, the knot has not failed. We don't have any cracking, load-induced cracking or failure around the knot. Another example of both tension perpendicular grain and shear. Let me turn my laser on. Let me turn my laser pointer on. There we go. So Down here, we've got tension perpendicular to grain as the deviated grain moves around the knot, and then right around there is shear failure. Up in this region is tension parallel to grain. That's where basically the failure would be initiated down in this area, and then you've got almost nothing left in terms of sound wood, but that's ultimately where the piece is going to get pulled apart. Again, feel free to unmute yourself and jump in with questions if you have them. Or if you want to save them, there's going to be a good spot later to start to have questions. Tension perpendicular to grain and shear failure. Again, shear failure along these long lines, and tension perp over here. Looks like tension parallel to grain right there. And the failed stick is kinked, which indicates that as a consequence of the knot being eccentric from the center of the stick, there was some bending involved. Right, laboratory tests in a tension testing machine. So basically grab the ends and pull them directly. Okay, Tom Neal provided these slides to show, again, the point. This is a grain deviation going through the thickness of the boards. The knots on either side of that kind of hide that grain deviation, so a grader may not even see that. So you got to wonder how these boards even made it out of the mill. Another case is we've got two spike knots emanating from the pith at this location, and they look like they're pretty much hidden. Maybe there's some surface appearance of that knot right there. But again, the point here, grain deviation created the failure of this thing, even without putting this thing in service. Okay, the definition of a knot is contained in the book on the left, the grading rules. A knot is, in quotes, a portion of a branch or a limb that has become incorporated in a piece of lumber. The implication of that is that the knot consists of all of the branch or limb that's in the stick, not just what you can see on the face. So it's important to consider the face measurements as well as the path that that branch takes through the stick. We assume that a branch grows outward from the pith in the shape of a cone. So I've got a perfectly cylindrical log here, the pith in the center, and as a branch grows out of this thing, it starts with 0 thickness at the pith and grows, its width grows linearly as it moves out toward the end, or towards the surface of the log. So if we were to cut a 2x4, for instance, out of this stick, then the knot that exists inside that stick looks like that. We only can see the face measurements, this one, that one, and these two. And we'll talk about, this will be the last example we'll consider. The point here is we assume that the knot takes the shape of a cone as it passes through the stick. What do you measure? The knot can have a variety of appearances. It can be circular, it can be elliptical, it can be long and narrow, it can stand upright, or it can lie flat. In order to measure a knot, you measure the spacing between two lines that are parallel to the edges of the board, or two longitudinal lines that enclose the boundary of the knot. So it doesn't matter what shape that knot takes between those two lines, just measure the spacing between those two lines. For example, an encased knot shown here, well, by definition, or first, an encased knot is a knot that's formed by wood growth around a dead branch. So you can see in this illustration that there's, you know, a small bark inclusion around this thing. You've got a break between the knot wood and the wood of the board. So it's pretty easy. That's why I have a check mark there. I'm confident that I measured the correct size of this knot. It's a little bit oval, it's a little bit angled, but it's the parallel or dimension between those two parallel lines. Pretty easy to do for an encased knot. Intergrown knots are formed when wood grows around and is intertwined with the fibers of a living branch. So the branch is growing at the same time that the wood is growing. And as a consequence, it's more difficult to assess the knot dimension. You can see at the top that we've got grain deviation around here, and the grading rules say that if there's grain deviation around a knot, you want to include that in the knot dimension. So a reference I found written by a former colleague of Ron's, is Joe Bodig, indicates that this grain deviation can be as large as 3 times the actual knot size. So it's important to look carefully for those details. Don't just think that you've got the knot going from about right there down to about right there. It can be more than that. All right, some other interesting pictures before we get into actual knot configurations. Tom Neal shared this one. We've got a knot that kind of hooks through a board. It's intergrown through most of the width of the board, and then it's encased on that outer top edge. Only just to point out what those two characteristics look like. Let's flip the board over and look at the back surface. Now, the change in tone or texture or reflectance of light or whatever one would call this might suggest to you that we've got high deviation of grain. So again, you got to look for maybe subtle clues that suggest that the effect of the knot is greater than its actual appearance on the board or on the stick. Okay, ASTM D245 establishes the principle that we use to measure knots. The text up in Times Roman you see at the top is a excerpt from that standard. And it says that knots in dimension lumber, I'll consider that to be timber as well, may be measured by the displacement method, in which the proportion of the cross-section of the knot to the cross-section of the piece is multiplied by the actual face width to establish the equivalent knot size. So writing that red statement in equation form, I'm going to say that A sub k is the cross-sectional area of the knot, which we'll have to determine as we evaluate each stick. B times D is the breadth times the depth of our stick, so that's the piece cross-section. The knot appears on the width or on the depth face, so I multiply by D, and that's the diameter, the effective diameter of the knot. So for any knot through the breadth, obviously the D cancels out here. For any knot going through the breadth of a stick, D sub k is the area of the knot divided by B. So we're going to imagine that every knot can be converted or equated to a cylindrical, an imaginary cylindrical knot. D sub k is the diameter going all the way through the stick. So, okay, perhaps the easiest one to look at is a knot that appears on 2 opposite faces of a stick. You measure dimension A, you measure dimension B, and logically, as you might assume, you average the 2, and that's the knot size. I'm not going to take that approach though. Instead, I'm going to divide this knot into triangles because that averaging approach doesn't work in every case. But if you look at area of triangles, then you have a systematic and method that will always work. Okay, so if we're looking at this stick, we see that face A, or dimension A, the knot appearance A, and we see the measurement B on the other side of the stick. But how do we know that it's a through thickness knot? How do we know that it's not two knots in a boxed heart stick that happen to be at the same point or same cross section? So it's critical to be able to identify that distinction. Is it indeed a through thickness knot, or is it boxed heart? And you've got two knots in the same space. Well, clearly you just look at the end of the stick, and if you can see the pith, then you know that it is boxed heart, and you've got two knots. If the pith is not in the cross section, you've got a single knot. That becomes a little more interesting if you're doing in situ study and you can't see the end of the stick. So you got to look for clues on the surface of the stick, or maybe some consistency in the other sticks, the other pieces of wood that are used in the building that you're examining to determine what kind of knot you have. If you can't tell, just assume it's a two-faced knot and you'll be conservative. Okay, so we have divided this knot into two triangles, and the sum of the triangular areas is A, the dimension A, the base dimension times its height, B, that's little b, and the dimension B times the height of its triangle, little b. Multiply those together and divide by 2. Then divide by B, the breadth, and you get the diameter of the knot is the average of the two. Okay, no surprise there. But the important implication here is that the largest dimension you observe, A, is not the size of the knot. It's the average of the two. You get a small savings in this case. Okay, moving on. What about a one-face knot? If you've got one knot that appears at a cross section, and the pith is visible at the end of the cross section, then you have a one-face knot, a single triangle, in a pretty simple case. So in order to evaluate the size of this knot, you have to measure the dimension A and the dimension P, the location of the pith going through the cross section from the face that contains the knot. We got a single triangle. The area of that triangle is A times P over 2. The knot size is the knot area divided by B, or A times P divided by 2B. Let's get rid of the B and let's get rid of the P and replace that with R, a simple fraction, P over B. That's the fractional location of the pith. In this case, kind of looks like P is about 3/4 of the way across the breadth, right? So we'll let R equal 0.75 for this one. So that means the diameter of the knot, the effective knot size, is R, a fraction less than 1, times the area divided by 2. All right, here comes, this is, let's see, how do we, I'm getting stuck here. Oh, there we go. The implication, a knot in boxed heart timber is much smaller than it appears on the face. If you're measuring the full size of the knot and saying that that's the knot size, you're being way conservative. The knot is never more than half the face dimension, and that will occur only when the pith is on the opposite face of the knot face. Basically, R is equal to 2, or is equal to 1.0. More commonly, though, we probably have the pith near the middle in boxed heart timbers. Let's say it's between, or somewhere in the middle third of the stick, in which case the knot size is somewhere between 1/6 and 1/3 of the measurement dimension. And you might think, oh, well, so what? That's, that's appealing, but how much difference does that really make? So let's do an example. I've kind of kludged up a cartoon here. Let's say I got a 10 by 10 box tart timber. So it falls in, by 10 by 10, it falls into the post and timber category for member sizes. I want to put a 6-inch knot on one face. So the face on the right. My pith is in the center of the stick. The diameter of the knot is the ratio R of 0.5 times the knot's measurement 6 divided by 2, or 1.5 inches. The grading rules for posts and timber are: for select structural, the max knot size is 2 inches. For a number 2, it's 5 inches. And for a number 3, it's 7.5 inches. So if we looked at this stick with the 6-inch knot on the face and called that a 6-inch knot, we might categorize our stick as not even satisfying number 2. It would fall into the number 3 category, somewhere between 5 and 7.5 inches. But in fact, our timber falls into the structural select category, or I'm sorry, select structural category, or it's even slightly better than select structural, than the limiting value of select structural. So if you use only box tart timbers, you can be done, because all the rest of the examples I'm going to talk about are for free of heart center timbers. But I think this should be a big takeaway. Might be a good place to stop and respond to questions if anybody has any. I don't see any on my screen because I've got my slides up.
There are no questions in the chat box.
Okay, let's move on then. Good. Okay, let's talk about spike knots. They come in 3 varieties. Category A, or case A, is a spike that covers the full breadth of the stick. That means that it covers the dimension B. It appears on both wide faces with measurements A and B. Case B covers the full breadth of the stick, but only appears on one face. Dimension B is 0. And then for case C, a portion of the breadth is occupied by the knot and only a portion of the wide face. The first 2 configurations could be found in lumber, but probably not in timber. And if you're going to have a spike knot in a timber, it's more likely going to be case C. Nevertheless, we'll look at all 3 of them. So we're going to get into a rhythm here. We look at triangles. The area of the 2 triangles is A times B over 2 plus big B times little b over 2. Factor out or divide out the B and you get a knot dimension of A plus B over 2 for case A. All right, pretty simple. For spike knot B, we're using B a lot here. The dimension B is 0, so the knot size is simply A over 2. And for knot C, we've got a single triangle of dimension A times C divided by 2. The knot dimension is A times C divided by 2B. Again, I'm going to let R equal the proportion of that edge. It's the ratio of the edge. It's the ratio of the knot coverage on the edge. So the diameter of the knot is R times A over 2. Okay. I'm presenting this for completeness. It's not particularly interesting, but I think it should be pretty clear. Okay, a 3-face knot. This is the one that everyone at the grading workshop shakes their head out and wonders, how does that work? And so this was kind of the motivation for doing this. The 3-face knot appears, well, on 3 faces, obviously the opposite faces, A and B, and then edge or face C with dimension C that's adjacent to A. In this case, we have 3 triangles with areas AB over 2, BB over 2, and C, dimension C times its height, which is this dimension over here, E over 2. So let's apply a little algebraic trickery, sort of thing that you hated in math class in high school. Let's multiply the third term by B over B. So instead of having CE over 2, we got CEB over 2B. I'm going to change to my marker. That's not right. I want a pen. Regroup the third term, so bring the E out front. Take C over B, and then B over 2. So that's the grouping. I want to combine the second and the third. Okay, so basically this B goes to there, and this B goes to there. Then I combine the second and third terms. I've got a B over 2 here and a B over 2 here. That lets me say B plus EC over B times B over 2 is that contribution to the knot size. And then I divide by the breadth B, and I get A plus this term divided by 2. So what we've been doing so far is we've been averaging for a knot that goes through the wide faces, or from one wide face to the other wide face, we've been averaging the knot size. So this is the knot size on one face. This is kind of a knot size on the other face. So here's how we interpret that. And we've got a little graphic to show that. Measurement C occupies the ratio C over B on the narrow face. That ratio is removed from the clear wood between the dimension B and the edge of the stick on the B face. So EC over B is an additional contribution to knot on this face. So our effective knot goes from this edge down here to now this dotted line. We have a 2-face through the thickness knot. The dimensions are A and B primed, where B primed is this thing. And then the effective knot size is the average of the 2. Is that sweet or what? Max smiled at least, so I appreciate that. Okay, let's repeat at least what we've done here. We've gone from a 3-face knot to an equivalent 2-face knot by saying this dimension C is adjusted to EC over B. Notice that this dark brown area above the dashed line looks to be roughly equivalent to the lighter area below the dashed line before you get down to the actual knot edge. That's the equivalence we're talking about. We're transforming some knot from one spot in the cross section to another so that we can do the average. Okay, in the grading workshop, we are told the rule, which is that we take a portion of the knot dimension, we take the knot dimension on one face and use a portion of the clear wood on the other face, add those two together and then average it. And it's, you know, you can do it a half a dozen times, but you still don't know why. The objective here is to help you figure out why. Okay, so here's the equivalence. The 2-faced knot with 3 triangles is equal to, I'm sorry, the 3-faced knot with 2 triangles is equal to a 2-faced knot with edge there and the dotted edge. Now, what a grader is looking at this, the grader is not going to measure the dimension C. The grader isn't going to measure A or B either. They do not carry a tape measure around with them just to be that precise. They look at it, they've done this often enough. They know a 2-inch knot versus a 2.5-inch knot appearing on the face. Instead, they're going to look at this and say, that looks like about a third, right, of this width. So they're going to take about a third of this dimension, and they're going to guess that. Let's say, well, that's 4 inches. So that's about 1 3/8. I'll add 1 3/8 to this dimension. That's probably 3. So I got 4 3/8 inches as my knot size there. I average that with what's over here, and I'm done. And it'll be pretty quick. It feel like a pretty casual process, but this is how it's done. A 4-face knot. Okay, we've seen this slide already, and that appears, this is where we get the 4-face knot by cutting a piece of lumber out of a big stick like this. You might or might not ever see this in a timber. So here we have 4 triangles, and I'm going to leave it to you all to do the algebra yourself. Suddenly a miracle occurs, and we get adjusted dimension A and adjusted dimension B, A primed and B primed, where A is adjusted by moving this dimension D over to this face, and then B primed is achieved in the same way we did before. The dimension C is moved over to use up some of the clear wood on that face. And as a consequence, the equivalent 2-face knot is again the average of 2 knot dimensions, but those dimensions are adjusted from what you actually see on the wide faces. Okay, we're just about done here with this discussion on measuring knots. So in summary, knot size is defined by the amount of cross-section that the knot occupies, not just the largest dimension on the face. The exception is a small stick cut from a huge log, in which the knot is indeed a cylinder of uniform diameter. So I guess in some respect, the title of this presentation, that knots are not as large as you think, that was supposed to be a hook to get you to sign on, and I hope it was worth the effort. That indeed, well, 64 of you are still out there. That's good news. Measuring knots does require that you pay attention to all characteristics of the knot. If we have to locate the pith, irrespective of how we measure the knot faces or the knots on the face, whether it's boxed heart or free of heart center makes a huge difference. In boxed heart, the knot size is incredibly small, and spike knots, they're generally pretty small, and they cause just, you know, a modest amount of impact on the capacity of our timbers. Even an edge knot, a spike knot on the edge of a bending member, relatively small effect. For the knot size of any free of heart center timber is in the average of the opposite face dimensions, and you might have to add or adjust those dimensions based on knot characteristics. That's not the whole story. So there's more to know. Other considerations are, where is the knot located? For beams and stringers, there's a difference between a knot that appears on the edge, meaning the narrow face, versus a knot that shows on the center, or I'm sorry, on the edge, which would be down along the bottom or the top, bottom or top of the wide face, versus one in the center. If it's not on the edge or it's not on the center, then you interpolate between the edge and the center limits. If it's a narrow face versus a wide face knot, there's differences on how it's done. If knots are closely spaced along the grain, you might have to assume they appear in the same cross-section. If there are, the knots are loose or decayed or checked, you might have to account for that. Decayed knots, for instance, basically say you can't have, you can't satisfy a number 1 or a number 2. Ron, I'll let you jump in here. If I have a small decayed knot, can I have a number 2? You might have to unmute.
In a timber?
In a timber, yeah. Can I have a decayed knot in a timber and still make number 2? I don't have my rules open here.
Yeah, I don't have them open either.
Well, why don't you? That's why you're on. This is primarily a
on here and
relation.
Tom on here.
Did you say that's why you're on, or that's why you're Ron?
That's why he is on the presentation.
Oh,
Okay, for a number 2 beam and stringer, knots must be sound, not firmly fixed, or holes, well spaced, are permitted. Doesn't say anything about decay. Unsound knots are limited to half the size of the other knots. Unsound means decayed, so there's a limit. Knot clusters, that's a bunch of knots coming out of the same spot in the pith that appear at the same cross section. So you got to consider that. So how do you deal with everything we just talked about? You take this information.
Before you go to that, Dick, there is a question from JD.
Okay.
What if you have multiple grades of framing members, let alone different species, used in existing structures? If you assume all wood species are the same, do you average the grade, take the worst grade, or some form of standard deviation?
I'm going to toss that to Ron. Ron has done a lot of in situ studies. I'd be willing to bet you're going to see a relatively consistent use of species, but grades obviously may vary. So Ron, what do you think?
Yeah, I mean, that's a good question. And, you know, what do you do with that? And most everybody that's on this is more interested in timber than they are lumber. Lumber, you've got a lot more sticks in a building, you know, a lot more floor joist than you would timbers. And so you kind of look at them a little bit different. You can look at them a little bit different. If you got timbers and you're grading them, then really the grade that you determine for that stick is the grade that you would assign to that. And what I normally do is, you know, work with the engineer to look at the load that's on that particular stick and see, does it work with that particular grade? When you talk about lumber, and now you're in a 5-story building, you've got 400 joists in there, you can start to get into some statistics because you got some load sharing and stuff that takes place if these are joists that are relatively close together that you don't have in a timber frame where each member is basically doing its own work. So in a timber structure, you would look at the individual grade on the individual stick, and you may have, you go through and you got a dozen girders, and 11 of them are select structural, one of them is number 2. You got to determine whether or not you can live with that number 2. It's easier to look at that with a group of columns. If you have a bunch of columns and they're well spaced, then most of those are select, high quality timber. Then you got one with, you know, huge knots in it that takes it down to a number 2. That one may not be able to carry the design loads that are assigned to it. So you have to look at the individual ones when you only have a limited number of sticks in the building. Does that answer that question?
JD?
Hey, Ron, this is John Dumsick. Yeah, thank you very much.
Okay, let's move on then.
Well, before we do, JD also says that have we discussed another timber grading class yet? And we haven't, but we will.
Indeed, that's the recommendation here is go to one of these things. Just to give you a little more idea of what's involved, there's a good balance between the regulatory aspects, meaning the rules that you see in those 2 books that I showed earlier, and then the scientific basis for the rules. Ron is, again, our instructor on the scientific aspects, but that doesn't mean he's not proficient in actually applying the rules. but it also carries, these workshops carry some cachet in that we have a certified grader there, and that goes on the certificate of achievement. You get tested at the end of it. It's not just to show up and get your participation trophy. You got to earn credit. And then you get a certificate that you can use for maybe a building inspector asking, well, what gives you the ability to say that this stick is a number 2? Well, here's my training credential. And then finally, there's a balance, a nice balance between classroom instruction and hands-on application of the rules. We roll a lot of timber. You got to look at slope and grain. You got to find the critical defect. Oops, the critical strength reducing characteristic. It's not necessarily a defect. A knot is not a defect in a tree. It's pretty essential to the growth of the tree, or the branch was. So we don't regard that as a defect. So if you're interested in a workshop, I'd encourage you to send Mac an email or send me an email. We'll collect interests and see if we can assemble an appropriate venue and timing and classroom. You know, with a limit on the attendance is somewhere around 20 people, and that's about right for 2 instructors to provide good support. Did I see another question come up or two, Mac? I thought something flashed out. You're muted, Mac.
No, not that I saw on the chart. You did get
Okay.
you guys did get a thank you from JD.
Okay, good. Another good place to stop for questions, if there were any. This is the TA Molten Barn in Grand Teton National Park, probably the most photographed barn in the state of Wyoming. Pretty spectacular site. It's on the National Register of Historic Places.
Say, Dick, if I can go back to John's question, the other part of what he had asked is if you have different species. You mind if I comment on that?
Go right ahead.
All right, so everybody that's on this call, virtually everybody that's on here, would look at what they've got. So if they've got eastern white pine and they've got southern pine mixed in the building, they're going to look at the grade of those sticks separately. Those that aren't as nearly as experienced as the people that are on this call frequently will make the mistake of the lowest, you know, the least common denominator. So they find something that's a low strength species, they'll apply that to everything, and they'll apply that low grade to everything, and then they'll do all these unnecessary repairs because they don't consider that they have a lot of other sticks that may be a higher strength species or a higher grade. So when you've got mixed species, you've got to at least acknowledge, okay, what do I have here? What's the grade? What's the species? But people that I work with that are in the guild and on the council, they always consider that instead of just lumping it in and saying, I'm going to take the least common denominator. Now, where's all my steel side plates?
To add to that, that question about mixed species is, first you have to identify what species you have. And thanks to Tom Neal, the Engineering Council has also sponsored a couple of species identification workshops. So if you're interested in that kind of deal, either a 1-day or a two-day thing, express that interest and we'll see what we can do about scheduling them. Very effective workshops. I see a question from Matt Hunter. Is there any discussion in these workshops about how a sawyer can make decisions to improve the grade of the timber they're cutting, specifically controlling slope of grade or slope of grain? Yeah, I think if you're specifying how a log is going to be cut and you can work with the sawyer in that regard, then locating knots so they appear midway on the face, on the wide face of a beam and stringer, for instance, is going to give you the highest strength if you have to use that stick. So orienting the log properly in the mill as it's being cut makes a huge difference. regarding slope of grain, if you're cutting timbers, my view is slope of grain in a timber is due to spiral grain, and you can't really do much about that. You're going to get spiral grain, at least in a boxed heart timber. Free of heart center, we're going to have spiral grain, but it's only going to be maybe on one or two surfaces. Let's see.
And the answer to Michael Schwartz's question is certainly. Certainly we can make sure and get the something set up. Ron and Dick and Tom and many of the people on TFEC know people all over North America, including Canada. So.
And the good news here is that the National Lumber Grading Authority, or is it Lumber Grades Authority in Canada, has signed on to what we're doing here with all the other grading rules writing agencies. So the grading rules are fundamentally the same, and no reason we couldn't get a Canadian certified grader to participate in the workshop. That would be cool. It would be a new. Okay, I've got a few more slides to talk about slope of grain. If we want to do that, Mac, you want to keep going?
Yeah, please. Yeah, yes. People are always free to drop off, and they do. So
okay,
I'd say plow ahead, sir.
Well, shame on them. Okay. So this is not a slope of grain photo. It's just a way cool knot that was in a piece of southern pine I was using to build a handrail or balusters for a handrail. So took a picture of that.
Did you use it?
No. Oh, next question. Can you provide the slides from this presentation? Mac has them.
Yeah, but if you saw today's e-blast, you have them. Just click on the line. So.
So Mac sent out an email that contains them. Okay, good.
Well, it contains a link.
A link
Yeah.
to them. Yeah, it's 3 or 4 megabytes or so.
Yeah, and we sent out TFEC 1, which Dick was the lead author on. And if you want to learn something about how to design timber frames, that's something you should at least flip through, even if you're not.
Okay, some definitions on slope of grain. Everything in italics here is a direct quote out of the WWPA documents. The slope of grain is a deviation of wood fiber from a line parallel to the edges of the piece. Clear enough? Slope of grain is measured over a sufficient length and area to be representative of the general slope of the fibers. And local deviations around knots and elsewhere are disregarded in the general slope measurement. So to apply the slope of grain, to determine slope of grain, there's a couple of approaches. One is if you have checks in your timbers, then the orientation of the checks will provide you a good indicator of the slope of grains. And we record slope of grain like we record roof slope, only we hope it's not that steep, like 1 on 8, 1 on 10, 1 on 12, 1 on 14, for instance. It's generally a 1 on something. So observe your checks and measure the rise over run. That's going to be your slope of grain. Another way to do it is get yourself a grain scribe. That's basically a needle on a pivot that is free to rotate, and then score a line on your timber. So you can, I think you can see, if you've got a big enough screen, a scored line on this timber with a little bit of frayed wood fiber. Get that needle into the grain and drag it, and it will follow the slope of grain. Do not rely on the boundary between the growth lines of the spring wood and the summer wood. That's not a measure of slope of grain. Another way to do that is to look at the tips of the V's on a flat grain face, and they generally follow the slope of grain. In fact, on this floor joist, the checks you see here tend to go right through the tips of the V's. They're close. So we've got relatively flat slope of grain in this timber. And then finally, yesterday I went out to Centennial, Wyoming, a little town at the foothills of the Snowy Range Mountain. On the way back, there was this herd of elk grazing about 200 yards out off the road. So I took a snap of that. Thought I'd close with that.
You're going to go hunting later this year?
Not this week, no.
No, later
Yeah,
this
if you have a mountain with velvet on it.
Yeah, later
No,
this year.
actually, I've got a lot of things going on. Of my 3 children, one of them is having his second child, and 2 of them are getting married. So we've got
Congratulations.
quite a lot of family activities, and yeah, the calendar is full. Thank you, Matt. Yeah. So slope of grain on this mountain looks like about 1:2.
Looks like about the angle of repose.
Yeah.
So, okay.
All right.
Yeah. Are there any other questions for Dick? What do you think is more important, Dick, knots or slope of grain?
It doesn't matter what I think is important. There's a controlling defect in every stick. And if you look at the grading rules, you'll see that there's a limiting knot size and there's a limiting slope of grain. And you have to look at which one controls. If your slope of grain is limited to 1/14 and you have 1/12, it's not going to be select structural, irrespective of knot size. So that's what the rules tell you anyway. Yeah, what causes the most concern for me as an engineer is slope of grain. But that doesn't mean that that rule applies or that perspective applies in the grading rules.
And what about knots? What about, knots in the context of notching for joists, let's say, notching a beam for joists? What about the context of that?
I suppose that's where we rely on the timber framer to properly lay out and move away from the knots at locations of notching. Peg holes, does that count as a knot? If you put a 2-inch trunnel into a timber going to be used in a bridge or something like that, does it count as a knot? Well, the good news here, there's no deviation of grain around it. So one would think, yeah, why not? Why not call that a 2-inch knot and apply that to the grading standard? I understand silent on that one. But then you're not an engineer, so you don't have to stamp it, right?
Correct.
That 2-inch hole, would it make a difference, Dick, if it's close to the top or close to the bottom or close to the end of the timber?
Exactly.
Or way out in the middle?
Yeah, top or bottom puts it in a higher stress region for a beam and stringer. So it could be regarded as an edge knot versus a center knot. Yeah.
Just to jump in, Dick, we want to make sure everyone is clear that there's a difference between grading the stick and looking at those natural growth characteristics like knots and slope of grain, and then looking at the effect of mechanical alterations. So it's really better not to treat mechanical alterations the same way as you would look at knots. Treat them separately. And that's why your comment that a hole drilled through a select structural post doesn't necessarily convert it to a number 2. You still have a good quality timber. You just have a timber with a hole in it, and you can look at the effect that hole has had on strength.
That's a good point, Tom. The grading rules are limited to what can be examined on the timber itself, and as we modify it, then we have to look at that separately. Looks like there's interest in Guelph as a workshop there. I will mention that the workshops we've had in Denver have been pretty well attended in terms of geographic distribution. We've had attendees from Canada, from South Carolina, from Washington State. There's an airport, international airport right there within a half an hour of our workshop. And our workshop in the past has been Rocky Mountain Joinery Center, which has got a huge inventory of material, automated shop, Hundegger equipment. So the workshop includes a little bit of tour of the yard as well as some demonstrations of the operation of that equipment.
Staff will do a little bit better job of supplying you all with coffee and lunch and breaks, etc. this time. Next time.
Yeah. Yeah, I got some bananas for this last time. I cut some apples in half. Okay, Andrew has a question. I have troubles finding the 2017 standard grading rules for northeastern lumber for the East Coasters. I would go to the Northeast or NELMA, Northeast Lumber Manufacturers Association website, and try to find it there. All right.
Okay. Well, Dick, again, thank you very much. It was very informative, very useful, and I sure am glad I saw it, and I suspect most of the people that are here today feel exactly the same way. So
good deal.
And just keep an eye on the next timber framing, because the article will be there.
That's right. Yeah, we were going to wrap up this article, get it to press, and it should come out in the fall edition. Comment from Helen Watts. Go to info@nelma.org for the NELMA book. Costs you $20.
That's right.
Get the interpretations, not just the rule book, but get the interpretations as well.
I'd also like to thank Ron Anthony, the wood guy, and Duncan McElroy from Fire Tower Engineered Timber, and Tom Nihil, formerly of Nihil Civic. Tells him he's retired. I'm not sure I believe him at this point, but at any rate, he's not retired from the guild, and thank goodness for that, because he's a major contributor over the years. So thanks to all of you tonight for this presentation and for the for the slides, the presentation, for the slides, and the upcoming article. Thank you very much. Good night, folks.
Stay safe.
Good night.
Thanks, everyone.
It's good to be with all of y'all. We'll do it another time.
We'll see you on the next one. Night, everybody.